Let's start today's sessions. The first talk is by Professor Jeff Oishi from University of New Hampshire. He'll be talking on simple models of moist convection, especially on linear dynamics. Thanks a lot, Jeff, for being awake for us. Please take it away.
Great. Thank you so much. Thanks to everybody for inviting me. It's really a pleasure to be able to share some of this with you. So what I want to do this morning is to talk a little bit about some of the work that we've done, me and my collaborators, but also a little more generally about why simple models are useful for moist convection. So to begin with, I just want to start by saying something that I think to this audience is very obvious. Atmospheric convection is extremely important, right? It powers an enormous amount of weather, particularly extreme weather, both in the tropics and up here at the mid-latitudes where I live. But one of the things that we have to remember is that if we come to this from a convection standpoint, as I do, I'm a physicist who studies pattern formation and non-equilibrium dynamics, so I think of convection as something like Rayleigh-Bénard convection, which is pictured on the right here of the screen, where you see some entropy fluctuations and vorticity. And if you look at that, if you compare that to, say, a convective cell, like an image on the left, taken in Colorado by a collaborator of mine, you'll notice that the distribution and the way in which we have the statistics are completely different, and the patterns are completely different. And the reason for this, of course, as we know here, is that moisture is key to this. When we release latent heat, you get extra buoyancy, and this simple physical fact dramatically changes the nature of convection from something that we think of. Now, that said, it's also worth pointing out that Rayleigh-Bénard is an incredibly helpful model. It's how we've learned an enormous amount about convection, but also about a lot of nonlinear dynamics and a huge amount of very important work from the very early work by Chandrasekhar, or at least summarized by Chandrasekhar in his famous book, on the linear stability, very well understood. That linear stability, even prior to the age of large-scale computing, led to a lot of thinking and ways of dealing with nonlinear saturation, which led to understanding of pattern formation. And it's a system that we can work with well enough that we can do rigorous mathematics on. So the Doring and Constantine results from 1996 is very important because this proves a rigorous upper bound on the transport that is possible from the Rayleigh-Bénard model, which tells us that what we can expect from a very mathematical perspective. I should point out that rigorous upper bound is a pretty weak upper bound, at least for right now. And that work is being work to lower the upper bound is ongoing. But nevertheless, the ideas here is that we've learned a lot about convection, even in systems where Rayleigh-Bénard is not the right model. So, for example, some of my collaborators work on highly compressible convection in stellar interiors, in the sun in particular. And there, Rayleigh-Bénard is also incorrect because the background density is stratified, and in fact, compressibility effects can play a role. In other words, there can be shocks within the convection. And yet, our understanding of Rayleigh-Bénard convection has helped us to understand all of these other systems. As well, it's a really nice base for us to add additional physics. So, for example, when we want to think about rapidly rotating convection, which is important in planetary atmospheres, it's also important in the Earth's interior. We have a system where the interpretability and our ability to rationalize and work with it mathematically is extremely helpful. So most moist convection studies use highly parameterized cloud resolving models. These include an incredible amount of physics and very, very high resolution computations that allow us to really probe the sort of dynamics of these kinds of things at large scales, and with a lot of detail. But these are not equally easy to interpret mathematically, and in some ways that limits our understanding of the underlying physics. So one of the things that I've been working on, and I think certainly I'm carrying on some of the tradition that has been going on for a very long time, is to think about combining moisture with the Rayleigh-Bénard convection. So here's the idea: is basically what is the smallest amount we can add to Rayleigh-Bénard convection to get something that approximates atmospheric moist convection, and yet retains some of our ability to do the same kind of mathematical operations on it that we can do on Rayleigh-Bénard to try to understand these things. So this has been going on for a very long time, as I said. Sort of a key early work in this is the work by Bretherton in the 1980s, which was then extended by Pauly and Schumacher about 10 to pushing 20 years ago, where they took the Rayleigh-Bénard convection model and they added latent heat release in a simplified prescription and assumed that there was never any prescription. So this is kind of a model of cloud formation and dissipation. You can also take the work done by Andy Maida and collaborators on their model, which they call the fast autoconversion and rain evaporation model, which takes the Rayleigh-Bénard, adds latent heat, and then adds rain and evaporation. So the rain, as it's falling, can re-evaporate back into the atmosphere, and so you have a system that has a fair amount of complexity. It's in fact the most complicated it's the most complex of the models that I'm mentioning here. And finally, most recently, is the so-called Rayleigh-Bénard model by Jeff Vallis, Doug Parker, and Steve Tobias from about 5 or 6 years ago, which takes Rayleigh-Bénard convection, adds latent heat, but instead of saying there's no prescription, it sort of takes the opposite. It probes the opposite limit from the Bretherton system in that the precipitation is instantaneous. And so in order to get a self-sustaining system, this has the same kind of idea for moisture that Rayleigh-Bénard has for heat, right? So in the Rayleigh-Bénard convection, heat is being pulled usually through the bottom boundary. And in order to, the energy that enters the system passes through the boundary. So the same thing happens here in the Rayleigh-Bénard model, because as soon as moisture condenses in that model, it disappears. In other words, it's assumed to precipitate out faster than any time scale that you're resolving in the model. So in order for there to be any moisture in the system at all, it must be diffusively transported up from a boundary. So this is sort of providing a kind of similar analogy to the way we think about heat in the Rayleigh-Bénard system. And I want to point out that each of these models have their uses, and in fact, we really have to study them in much more detail. I think there's a lot left in this approach that we don't understand, and comparing how these models behave under similar forcings is, I think, really important. And also, I think from a mathematical standpoint, one of the things that I've been curious about, and I think is a really interesting area for future work, is combining and understanding in what ways can we take sort of a bigger model than any of these, and derive all of them from it, and try to compare and contrast what exactly we get from these. So there's a lot, I think, that can be done. I'm also sort of, I was asked by the organizers to sort of be a bit pedagogical, so that's why I'm going a little slow, but also I want to highlight what I think are some really exciting problems that I think that students and postdocs and people who are interested in some of this more mathematical sort of thing can take. So I'm going to highlight a lot of different projects as we go through that I think would be really interesting for someone to explore. So I'm going to focus on the Rayleigh-Bénard convection model for the rest of the talk, just to give us something concrete to talk about. It's also the thing I know the best. But in many ways, it shares a lot of important features with some of these other models, and in fact, other models that either I'm unaware of or one has yet to come up with. So, okay, this is a lot on this slide, so I'm going to spend a fair bit of time here. So one of the things that I want to point out is, let's just take a look at the equations here. So the first three are exactly what we would have in a Rayleigh-Bénard convection. They're modified. They have they have one additional term in them. That is to say, the momentum equation is literally identical to Rayleigh-Bénard or even fluid mechanics with any buoyancy in there. So I've written these in a bit of an idiosyncratic way. I've written all of the linear terms on the left and the nonlinearities on the right. That's to help clarify a little bit of the different physics, and we'll come back to this as we come back and talk about these things. So we've got our Navier-Stokes equation with a buoyancy term. Then we have continuity. We're assuming we're incompressible here. Again, this is in keeping with the spirit of these very simple, what can we take from Rayleigh-Bénard. However, I should point out that anything about this model here can be extended to, say, an anelastic model where you have a density background stratification that's important, even if there's no dynamical compressibility in the system. So something that filters out sound waves, one of the so-called soundproofed models that we like so much in atmospheric dynamics. You could absolutely adjust you could absolutely rederive this in those cases, and it carries over in a very similar way. I've done that, but I've never really explored it very much. So continuity, divergence free. Then we have a buoyancy equation, and this looks almost exactly like the Rayleigh-Bénard buoyancy equation with one additional term on the right-hand side. Now, this is a nonlinearity where we have gamma times something c. Okay, and then we have to add another variable. Of course, we have to track the moisture itself or the humidity. So in this case, we're using relative humidity, which I've denoted with Q. Now you'll notice that the humidity term, like the buoyancy equation, also has a diffusive component. And to be completely formal here, we've left the diffusivities different between buoyancy and humidity, and I'll come back to why they're in these weird script letters in a second. But you'll notice, again, the humidity has this C term, but without the gamma and also with the opposite sign. So let's now come to what that C term is. That's the condensation rate. Okay, and so what we have here is the condensation rate is simply equal to the amount of condensation you have above the saturation humidity. So Q minus QS. QS is the saturation humidity. We'll come to that in a second. And then we have this H here, and that's a Heaviside. So this is a Heaviside function. It's a step function. So it's 0 when Q is less than or equal to QS, and it's 1 when Q is greater than QS. And then we divide that by a timescale tau. And if you just focus on the humidity equation for a second here, I think I can use my mouse. So the humidity equation here, you'll note that C is balanced by dq dt. So this must have dimensions of Q over time. The Heaviside is dimensionless, so this Q minus Q, of course, Q minus QS is in terms of Q, and therefore we divide it by some timescale tau. We're going to come back to that tau in a second. That is the first of our completely numerical parameters that exists in this. It has no physical meaning whatsoever. It's just a timescale that we have to use, and we have to make it fast in order to satisfy the conditions that the Rayleigh-Bénard model states. So, of course, we have the saturation humidity, which is a part of the physical background. In this case, we've simplified the Clausius-Clapeyron relation as much as we can, get it down to an exponential. So we have exponential times alpha, which is some coefficient, times the temperature. And finally, the temperature here is related to the buoyancy by the background stratification, the background temperature stratification, which is linear in this case, very much like Rayleigh-Bénard convection. We assume that you have a fixed temperature on the bottom, you have a fixed temperature on the top, and the background state of temperature is linear, connecting those two things with the slope beta. Now, there's one additional piece of information that we need here to close this thing off, which are the physical parameters of the system. So let's come back and talk about those. So I've non-dimensionalized this in a particular way. We can talk about that if it's interesting to people, but we've used a buoyancy timescale. In Rayleigh-Bénard convection, there's a reason to do that. In traditional Rayleigh-Bénard, it's usually just a choice of convenience, and it doesn't really make any mathematical or physical difference. In Rayleigh-Bénard, the situation is slightly different, and so this particular choice is somewhat helpful, certainly in certain circumstances. So we have a reduced Rayleigh number. So that's the traditional Rayleigh number. We have the Prandtl number divided by the Rayleigh number to the 1/2 power. The Prandtl number is the usual ratio of diffusivity. So it's the ratio of viscosity to thermal diffusivity. And then we have buoyancy and moisture diffusion parameters that are also combinations of Rayleigh and Prandtl numbers. Now, like I mentioned at a couple minutes ago, we have chosen to keep this as general as possible, though usually, and you can kind of see why this is true, moisture and buoyancy are usually going to diffuse at relatively similar rates because the thermal diffusivity is usually of the same order of magnitude as the diffusivity of a tracer particle within, which is the moisture. Nevertheless, this is the sort of full system, and then the final physical parameter that we have is the gradient ratio. So that's the ratio of the background temperature gradient to the scales, the physical scales in the problem. So We also, in addition to those are flow parameters. So those are things that we can change, that can change in a model. These are things that are not fixed. However, we're dealing here with moist convection. So of course we have to deal with the physics of water. And if water is your condensable, then these two parameters on the right are fixed. You don't get to choose them. So there's the latent heat release. This is a dimensionless measure of the latent heat, and the dimensionless temperature fall off in the saturation humidity, so the Clausius-Clapeyron. So those two things are fixed by water. We can't change them. They're 0.19 and 3.0 in these units, or these dimensionless system. Okay, so that's a lot, but that's the basic idea. And so let's come back now before we close off this slide and just focus again briefly on the condensation rate term and the differences here. So you'll notice that it has no the only difference between what happens in the humidity and buoyancy equations is that the buoyancy is multiplied by gamma, and that's because there is a fixed amount of latent heat that gets released as condensation occurs. Now, the amount of condensation is proportional to the amount of supersaturation, but of course that's always going to be close to 1, and that's the job here of the Heaviside function. So when it's less than when it's less than saturation, there is no condensation, and so there's nothing. When it's above saturation, tau is is a very fast time scale, so this is a very large amount until it will pull itself right back to being below the saturation, because the humidity here has a negative condensation rate. So as condensation becomes supersaturated and falls out, the relative humidity drops, and that lowers you back down until the Heaviside shuts you off. Now, similarly, in the buoyancy here, the condensation itself doesn't contribute to the buoyancy, but the latent heat release, which is proportional to the amount of condensation, does. So we have this sort of gamma C. So that's the real most important physical parts of the system. In fact, it's the only real difference with Rayleigh-Bénard. So let's continue now to talk a little bit about how we can use this model and how we can rationalize it. So before we continue, I did sort of allude to this with the tau parameter, but there are two numerical considerations that are inherent in the Rayleigh-Bénard model. The first one you see is explicit in the equations. That's tau. That's the time scale over which the condensation rate happens. The only criterion there is that it must be much smaller than whatever your minimum time scale is in your model. So if you're doing a nonlinear simulation of this, that would be the time step, the smallest time step in the problem. When you're doing linear dynamics or some sort of analytical calculation, it's the smallest time scale that you're going to. You always set it smaller than the smallest time scale, or one over the biggest frequency in the system that you have. So if you're thinking about waves or instabilities, growth rates, these sorts of things. The other thing that is hidden in the equations themselves, as I presented them thus far, is what you do about the Heaviside. So the Heaviside function can be used as a step function. So you could actually have something in your system, in your numerical system, where if Q is less than QS, you simply turn off the condensation rate. However, if you're trying to do analytical work, then you need some sort of way of rationalizing this so that you can subtract it, you can set it into a background about which you can linearize. And for that, you need some sort of mathematical approximation to a step function that has a finite derivative, but hopefully a very large one. And the choice that we made here is 1/2 times 1 plus the error function. And the error function itself has a parameter that tells you how wide it is. In other words, over what range does it take the slope from 0 to 1. And so that's another numerical parameter, which there's a considerable amount of, we took a considerable amount of care in trying to figure out what to do with it. I won't bore you with those details, but we wrote about it extensively. Excuse me. So just as an aside here, I want to talk a little bit about how we solve these equations, both nonlinear simulations, but also the linear dynamics. And we use this PDE solver that I've been on the development team of since 2011, which is called Daedalus. And the thing that's nice about this is it allows us to add equations in by text. So at the top here, you see this is actually just regular Rayleigh-Bénard convection. Where you can see that you simply enter in divergence U is 0. Here's your Navier-Stokes equation. I left off the buoyancy term. No, this isn't. Never mind. This isn't Rayleigh-Bénard at all. This is just Navier-Stokes. Okay. Nevertheless, there's a lot of really cool stuff you can do with it. It's open source. You can go find it on GitHub. And if you have any questions, don't hesitate to email our mailing list. We try to be very helpful to people, especially newcomers to the code. And I should say the code itself has nothing to do with convection or even fluid mechanics. It's a completely generalized partial differential equation solver. So there's loads of different things you can do with it. Okay, that plug aside. Let's come back and talk about the linear background solution. So what's the stationary solution about which we might want to try to study stability, right? So if we want to understand a problem like when does convection set in, what are the linear stability properties? In order to do that, we need to know what the background state is. And while I mentioned that the temperature background is fixed in the sort of Rayleigh-Bénard sense of being a linear gradient from bottom to top, hot on the bottom, cold on the top, what is the background of the moisture? And that actually is a more difficult question than it might first appear. So in their 2019 paper, Vallis et al. Derived what they call the drizzle solution. And this is called for good reason. And the basic idea here is that moisture is diffusing across the boundaries. It gets wicked up into the atmosphere where it crosses the saturation point and rains out immediately. And so this is a background stationary state. Everything is in steady state. So in this limit, we take d by dt to 0, and we say that the velocities are all 0. So if you do that, in that limit, you have only these terms left. You have your buoyancy equation, which is diffusive, and your humidity equation, which is diffusive. Everything else sets to 0. So for simplicity, and in fact, there are reasonably good physical reasons for doing this, but even if there weren't, we'd still do it. We're going to set P equal to S, so we can drop those both out here. And now we're going to define a moist static energy. This is a new quantity, M, which is equal to the buoyancy plus gamma, which is, remember, is the amount of latent heat per condensation, times the humidity. So if you add these two equations together, you end up with a very simple equation, which simply says that the Laplacian of M is equal to 0. Great. Okay, that seems like it shouldn't be very difficult, except remember, hiding in this expression is the saturation value of the saturation humidity as a function of temperature. And so this actually ends up having an analytical solution that you can find in terms of the Lambert W function, which is a special function. It's not terribly difficult to work with, but it is not the simplest of solutions in the way that the background state for Rayleigh-Bénard is fully specified by a single linear equation. Okay, so we can take a look at what some of these things look like. And so these are static atmospheres. So we're going to start with atmospheres that are fully saturated. So there's a lot of lines on this plot. So let's start all the way on the right over here where you see this light blue line. And that light blue line is pegged at 1. So we have the Z here. This is the height in the atmosphere on this, on the up and down axis. And then the x-axes of each one of these plots are specified by the quantities in question. So we have temperature is the magenta line here. We have Q is the humidity, and the blue line over here is the relative humidity. And so this is 1 everywhere, meaning the atmosphere is everywhere saturated. Okay, so with that, we can now let's go from the furthest right line all the way over to the left subpanel, where we have three families of curves here. So we have a bunch of curves that are in red tones, a bunch of curves that are in blue tones, and then a black curve, which is just 1, of which there is just 1. So the red toned curves here are the buoyancy. So it starts out at 0 at the upper boundary. And for each one of these things, it comes up, and for the lowest beta case over here, it turns back down. So the gradient of the buoyancy itself is positive here and negative there. And this is true for these as well, though to a lesser extent. The M is the moist static energy, and you'll notice that the moist static energy is a much straighter line. In fact, it is exactly a straight line, we'll come to in a second. So as this beta parameter goes up from 1 to 1.2, we see a behavior change. And that behavior change is much easier to see if we, rather than look at the quantities themselves, we look at their gradients. Okay, so over here in the middle panel, now we have regions where we have the gradient of the moist static energy in blue, the gradient of the buoyancy in red tones, and the gradient of the relative humidity here the total humidity, not the relative humidity. The relative humidity is 1 everywhere. This is what the humidity actually is as a function, but the gradient of the humidity is. Okay, so the gradient of the humidity here is independent of beta, which is why it's just one line on these two things. So, okay, what do we have? What we have here is, we'll notice that the buoyancy here starts off with a positive gradient and then crosses 0 and becomes negative. Similarly here, this one starts off positive, crosses over, becomes negative. And these two are positive everywhere in the domain. Now, it's a very different story for the moist static energy, M, right? The gradients are all constants, which is how we actually can tell that, in fact, not just the blue lines on the left panel don't just look straight, they actually are straight. And so what we have here is the moist static energy is in the limit that there is no diffusivity in the problem, it acts as the ideal stability boundary. So with the gradient of moist static energy is negative, the system is unstable. And so you'll see here that in this case, if you didn't have moisture, you only had this buoyancy background gradients, you may or may not be unstable. But the sum total of the two is unstable in all but this lightest case, the beta of 1.2, which is stable here. Okay, so that's the background solutions. They're complicated, right? This is actually already kind of an interesting phenomenon here. So this entire atmosphere is saturated. Okay, so what we do here is we specify that the humidity at the bottom of the atmosphere is equal to the saturation humidity. Okay, so here's just a sort of we have these two parameters physically. We have gamma, that's the amount of latent heat released per as a function of condensation. And beta here is our background gradient parameter that tells us about how the temperature and moisture gradients in the background behave. So as I mentioned at the beginning of the talk, gamma isn't something you get to vary unless you go to another planet and you're dealing with a different condensable. So these lines are here all at the value of water. This triangle over here is relevant to some of the condensables in Jupiter's atmosphere. But we'll leave that aside there. It's just there to remind you that there are other possibilities. But for Earth, we're stuck on this line over here. And so in this case, we have, as beta becomes larger, we push into a completely stable region. But here, you see that there's a wedge in between where the moist static energy is 0 and where the buoyancy, the dry buoyancy, is stable. So here we have something that is what we call conditionally unstable. This is well known in moist convection, but here we've sort of come up with a simple model that reproduces these sort of behaviors. And then below this line here, it's completely unstable. So even if you had no moisture in the system, you'd be thermally unstable. Okay, so there's also interesting questions of what happens when the atmosphere is not fully saturated, and that's interesting for a couple of reasons, which I'll come to shortly. But I'm not going to go through all this the same. It's the same basic idea here. It's just that now the dashed line represents where the relative humidity has not yet reached 1. Okay, so this is unsaturated in the bottom of the domain and becoming saturated at altitude. And so the basic ideas are all sort of similar here. The solutions are become much more complicated. You'll notice here that you have this sort of discontinuity here in the way these behave. There's a lot more to the system itself, and I should just note that the boundary condition here is that the buoyancy at the bottom is 60% of saturation. And that's just sort of a choice that we made. It's partly something that Vallis et al. Had done, and then we were sort of using that and generalizing it to sort of talk about the stability. Okay, you can play the exact same game here when you have an unsaturated atmosphere. You have 3 different regions, an unstable, a dry stable, and moist unstable. So that's our conditionally unstable regime. And then we have a stable regime. So let's now think about these things, and that's a very basic kind of stability, right? That's the sort of basic energy stability of the whole system that I just showed you. Now, in a real system where you have diffusivities that matter, you need to overcome those diffusivities in order to become unstable. So it's not just a simple gradient number is not the only thing that matters. So the real power of this model, of course, is that we can linearize it properly, come up with a background solution, linearize around that background solution, and solve an eigenvalue problem to understand the stability. And so we do that in a very standard way, where we take all of our variables and we assume that we have some background state F0 and a perturbation about that perturbation about that background state. Now, the background state and the perturbation can both be functions of space and time. And here we're going to choose a linearization, which is just another a formal way of stating that is that F1 is of order epsilon. So it's a small amount. I guess a more formal thing I would say is F1 over F0 is order epsilon. And then we take the typical Fourier ansatz here, where we assume that we're periodic in the parallel direction. So along the surface of the Earth, we're just going to assume periodicity, but we can't do that in the vertical direction, of course. So we have some eigenfunction f hat, which is a function of z, and then we take the Fourier ansatz for the spatial and temporal component. So omega t minus I k perp times x perp dot x perp. All right, and so what we're going to do here is that if we plug this in, we're going to end up with an eigenvalue equation when we plug this ansatz into the equations that we had before. We're going to look for something with a complex eigenvalue. Omega is going to have both a real and an imaginary part. And you'll notice in our convention here, the real part will be the growth rate. So if omega r is positive, it will be exponentially growing. If omega r is negative, it will be exponentially decaying in time. And then there's also the possibility, of course, of a complex part of the equation as well, where you might have waves at the same time. Okay, so I'm going to keep an eye on this time here, just finishing up here. There's a lot of very tricky mathematics that has to happen here. I'm going to skip over this, but it turns out that linearizing this Heaviside function, which remember required us to use the error function, or we chose the error function in order to make this easy. It's not that easy. Once you've done that, there's a big penalty for doing it wrong without a doubt. So if you don't do this asymptotic expansion properly, you end up with a 20% error in the critical Rayleigh number. So the when it's onset. So it's not a small effect. So finally, once you've linearized around this background state, you end up with a set of linear equations, which are going to end up being an eigenvalue problem. There's this non-constant coefficient, which script n here, which is simply equal to the rationalized version of the Heaviside function. So the one where we put a function in there. Okay, so what's the stability? What have we found when we do this? The first thing, and this is quite interesting, is that the onset is direct, just like in Rayleigh-Benner convection, meaning that at onset, there is no wave motion in the unstable mode. The other thing is that when we now have this conditional instability, right, where we can, where we have the possibility of having only moisture, we need both moisture and buoyancy to make the system unstable, whereas in the unconditional case, it doesn't matter what the moisture is doing. The thermal background is enough to do this. That changes the critical Rayleigh number. That is so the Rayleigh number measures the driving of the atmosphere. So how important is the temperature difference between these two things? Or how big is it in a dimensionless sense? Conditional atmospheres are 10 times more stable, is one way to put it. So it's a very big difference. And we can now, with all of this machinery, we can now run through these plots. These are linear eigenvalue problems. They're very easy to solve. They're very cheap to solve. And we can do this very rapidly and think about this. So here we're comparing two different values of gamma. Again, on Earth, you don't get a choice. So just look at the blue curve. And we can run this as a factor of beta. And we see that there's a limit here where this appears to be approaching a beta beyond which it becomes stable. And that's exactly what we would expect. That's another way of saying that here we have there's no energy gradient. It's not possible to be unstable. The other thing here, the circles are the critical Rayleigh numbers. The squares are the critical wave numbers, and the only thing to note here is that they're almost perfectly flat. They don't really change. Okay, so we can ask ourselves, what do the fastest growing modes look like? I'm running out of time here, so I'm actually not going to focus on this, but I want to point out that the disturbances here from the linear theory, we can now go and look at these and see what these perturbations, if these linear perturbations are actually imprinted in, say, a numerical simulation, or perhaps even in the atmosphere itself. Unconditional and conditional don't look radically different here. The only difference is the relative amplitudes of the velocities. So here in the conditional instability, the x velocity is both velocities are much, much larger, which is interesting. Okay. Now, the unsaturated atmosphere becomes very interesting for the following reason. I think this is the sort of payoff for all of this kind of work. So one of the things that we were able to find using a simple model like this is the onset is still direct. So when the mode goes from being stable to unstable, it does so at a point where the growth rate is exactly 0 and the wave frequency is exactly 0. However, once you have a mode that crosses and becomes unstable, in Rayleigh-Bénard convection, there are still waves present in the unstable atmosphere. That's completely unlike the traditional Rayleigh-Bénard convection. Once you get omega r crossing 0, that is to say the growth rate A mode becomes unstable, then the frequency of gravity waves in the atmosphere, the Brunt-Weissele frequency, becomes imaginary, and there simply are no waves at all. So you have, if we look at the spectrum, and this will be, I think, where I'll stop here. Just focus on the plot on the far right. These are all just sort of pushing from critical into this is just making it more and more unstable as you go left to right. So on the right here, we have the most unstable case. We actually even have multiple modes are unstable, the red dots here. So the plot here has the growth rate on the x-axis and the frequency of modes on the y-axis. So the instability being direct means that the mode here that's becoming unstable, so this is exactly at really critical. So this has 0 frequency and 0 growth rates, orange here. As you continue to turn up the Rayleigh number, you end up with a unstable mode, but the blue points here are waves that continue to persist in the atmosphere. So these have finite frequencies. They're damped, but that's because we have viscosity and diffusivity in the system. And those persist as far up in Rayleigh number as we've seen. So that's very interesting and quite different. And I think this is a result that would be very hard to tell from looking at numerical simulations. So there are many, the unstable modes look quite different here. This is, by the way, is in an atmosphere that's only partially saturated. So just so we get the punchline across. And finally, if we look at these things, the stable waves that we see in these systems look like gravity waves. So here, the black line is the unmodified gravity wave frequency, non-dimensionalized here appropriately. And the modes that we get in our unstable cases, these are the stable modes, look like moisture modified gravity waves. And in fact, we've done some more things to sort of convince ourselves that that's the case. But I'm going to stop here. With just one last thing. So could these waves be excited by plumes, even in fully saturated atmospheres? So in a fully saturated atmosphere, we don't see these waves in the linear spectrum. But remember, when you have a plume in a saturated atmosphere, that plume dries out the area around it, which means that it's now no longer fully saturated. And that allows the possibility of these waves running around in those atmospheres. So there's a lot of really interesting work. I'm just going to leave this up here to sort of, if you have any questions, or I can pass these slides on so you can have a look. I'd say we could discuss it at the conference, but unfortunately, I am not there. So I hope this is helpful to everybody. I hope this has been pedagogically useful for everybody, or at least maybe has spurred some of you to think a little bit about how we can, how these kinds of models can be helpful. So thank you very much for your attention, and I'd be happy to take questions.
We have ample time for questions. Thanks a lot, Jeff. I'm passing the mic around.
Okay.
Michaela has a question.
I was saying, can you bring it down a notch for somebody who's not as mathematically inclined and actually answer your second question? So how do we use this to explain convection in the atmosphere?
Right. So let me let's see. Okay. So one of the things that we've done, can you see the movie?
Yes.
Okay. So this is, I think, is sort of what all of this is sort of building to. So this is a nonlinear simulation of the system, but now what we're seeing here are plumes that are being set off, and those plumes are driving these waves into the atmosphere. So those waves, which, as you can see, as they propagate, they're easier to see in the relative humidity fluctuations. They propagate across, and in fact, they cause very large-scale changes to the atmosphere as they get pushed around. The dynamics of those waves are predicted by the linear spectrum that we had derived before. So this is still a very, very simplified model of the atmosphere, of course, but I think the point is that in studying these models, I think what we can gain is at least a sense of how we can understand the interaction, the sort of strong nonlinear interactions that we have in these systems and how they can be rationalized by and perhaps explained by some of the linear dynamics that are going on within them.
Thank you.
Thanks for the great talk. So you showed the results based on like eigenvalue analysis. Do you have any plans of doing like non-modal like analysis of these equations to kind of gain some more insight in how perturbations are growing?
Yeah, okay, so that's interesting. So typically, just for some context, the non-modal analysis is something where instead of considering just the eigenvalues of the system, you think about regions where the operator also is not infinitely singular, but is very poorly conditioned. So for systems that have shear in them, strong shear in them, we know that the linear operators are very strongly non-normal. And that leads to transient growth, so things that are not formally unstable, but whose eigenvalues can reach, stable modes can reach very high amplitudes before ultimately decaying away. So in these sorts of situations, you can have very interesting behavior. Now, the interesting thing is that the Rayleigh-Bénard model of convection is normal. If you look at the operator, the mathematical operator, it's completely normal, and the spectrum has no the pseudo spectrum. So that's the generalization of the spectrum. Is completely just a series of infinite points. So one question that you could ask, and I think it's a good one, is to what degree does the operator become non-normal when you add in moisture? And the answer to that question is I don't know, but I think it's a really interesting question, and I think it would be pretty easy to get started on that with the tools that we've developed. I should point out that we also have a bunch of open source tools for solving eigenvalue problems that do include non-modal analysis in the form of pseudospectra. So I think that's interesting, and I don't know.
Yeah, thanks a lot.
Thank you for a nice talk. I'm interested in the convective organization, so I'm wondering if this simplified Rayleigh-Bénard convection framework can be extended to include evaporative cooling or radiative cooling. So I don't think it is reasonable next step, or how do you think?
Absolutely. Someone has actually already done this. There's a paper. I can get it to you. I don't have the reference off the top of my head. Someone has added radiative cooling to the model and found actually multiple groups have. So I know that Greg Dritchell has done some work on that along with these folks, no longer at Leeds, but formerly. They've done some work on this, some linear work, kind of an extension of this, including radiative effects. And then there's another group in Europe that I cannot remember the name of, but I can pull up the citation. So that is absolutely something that people are working on. as an extension, as in some cases a very simple extension.
Thank you so much.
Hey, hello, this is a nice talk. As a forecaster's perspective, I'm just wondering that just mere the presence of conditional instability doesn't guarantee deep convection, and the models, especially the NWP models, are failed in this case. So, how do we explain this? Conditional instability, based on the conditional instability, how do we explain the moist convection?
Yeah, so I think one of the things that I think these kind of models can help with is exactly the sort of point that this sort of movie is making. This movie is making, which is that when you have conditional instability, the background can be order 1 modified by perturbations, by plumes and perturbations that I think we could try to get a better understanding of using a simplified model where we have far fewer knobs in the model to turn. And I think that's sort of a really interesting question. So one of the things that you can sort of see in this movie is that it's sort of approaching like a limit cycle type behavior, where it's kind of, you can look at the relative humidity gets very, very high almost everywhere across the domain. Plumes go, waves travel through the domain, and lower the relative humidity. So there's just a lot of really complicated dynamics, even in simple models. So I don't have a direct answer because I don't know, but I think that this sort of model is could be an interesting way to look at this, to those kinds of questions, those exact kind of forecasting questions. Yeah.
Yeah, thanks, Jeff. Vishal from IIT Bombay here. I was just thinking, so looks like the background state, both in terms of thermodynamics as well as the background velocities that you may have, gets kind of reset after the growth of instability and waves both. So I was just thinking, what about the coupling between convection and momentum transports? Because in the observations, people have seen that as the either shallow or deep, the convection triggers gravity waves very quickly. I mean, that's the fast response. And they also help set some mesoscale circulations, which take part in associated momentum transport. So I was looking at your animations and your stability analysis. I felt maybe there is something to learn about the coupling between momentum and heat transport here.
Yeah, no, I think that's true. Another thing I know, so Jeff Fallis has worked on this a fair bit of looking at slightly larger scales than these. So these are very small scales. I mean, so one thing I should say also is that when you're thinking about building off of a Rayleigh-Bénard background, remember we have a very, very unrealistic background state that we start from, because we're considering very, very shallow layers here, and not just shallow in aspect ratio, right? I just mean like you can't model deep convection with this because to do that you need to actually have the density background fluctuating, which we don't, or not fluctuating, falling off with height. So two things. I think one is, like I said, I think there are very straightforward ways to modify this to anelastic approximation, where then you could actually study deep convection directly. The other thing is on slightly larger scales, Jeff Fallis has been thinking a bunch about how these sort of structures propagate. So that's not quite getting at your question of momentum transport, but I think it's moving in the same direction when you start thinking about what sort of self-sustaining large-scale structures can you get. So sort of large-scale cyclonic activity that meanders. That is in some sense a form of momentum transport. And I think a lot of the work that they've done on that was sort of predating some of these Rayleigh-Bénard models, and I think now that we have them better situated, I think moving back in that direction could be really very interesting. So I know that's not a very satisfying answer, but I do think that it's something that could be done.
Yes, thanks a lot. Thanks, Jeff. Let's thank Jeff again. And thanks, Jeff. See you around.
Okay, take care.